Hi, Year 12s. So here is my bit of an introduction into subtopic 2.3. Now, the first part is talking about flowcharts. So this is sort of like almost a chemical engineering sort of part where we talk about um, how we can get from some raw material through to a final desired product through often through multiple stages that you know every single type of process we're doing is going to have a different flowchart, so it is quite varied, and I've got one example down here. Now, to start with, just going to mention that pretty much everything that we interact with on a daily basis has been processed in some way, and so that's why this section is looking at some of those processes. Now, one of the components we need to worry about is the raw materials. So these are the substances that we start with. Often they're going to be unprocessed. They're going to be raw. They're going to something you dig straight out of the ground, for example. An example would be crude oil or some sort of fuel. It could also be a mined mineral, so something we dig out of the ground that we have to process further before we can use properly. Now, during the process of, during the processing of them, you will often have some sort of waste product. So that will be something that comes out of our process that we do not have a use for. So it comes out, we don't use it, and there is no feasible use for it, or at least in the particular flowchart setup, there is no use for it. Now, I'll mention just because something is a waste product doesn't mean there can never be a use for it, but they usually just need to be gotten rid of. Now, byproducts. So this one here, when you have a particular process that you're doing, you're often going to make some other substances which are not the final desired product, but they are something that we can make use of in some other way. So be that you can it's a material that someone else might want, or you could use it within your process. Like, for example, if you need to heat stuff up, and one of the byproducts of a reaction is some excess heat, you could use that heat to heat the earlier stages. Now, here's an example flowchart. So this is an example from an old exam paper, and we're going to use this to sort of help explain what we're seeing. Now, over here, we start with our raw material, which in this case is a fossil fuel. Now, what we're going to try and do is we're going to try and get from this fossil fuel down to electricity, which was our product. So products don't necessarily have to be like physical stuff that you can hold. It can be getting energy out of a particular reaction. So we take the fossil fuel and we put it into a combustion chamber. So we're going to be burning it. Now, as you know, when you burn fossil fuels, you're going to get exhaust gases coming out as products of those combustion reactions. Now, those products of the combustion reaction, in this case, those exhaust gases, are waste products. We don't necessarily have a use for them. Now, technically, you could do things with them, but in this case, usually you just get rid of them. Or in this case here, we put them into a separate stage that's pollution control, just to make sure we're not spitting it straight into the environment where it can cause harm. In a car, for example, this might be something like the catalytic converter to do some further reactions. Now, for the main set of reactions, we have a combustion chamber, and that is connected to a boiler. So this boiler is going to use the heat from that combustion chamber to heat some water. Now that water is going to, once it gets heated up enough, it'll turn into steam. And it'll power a steam turbine or spin a steam turbine. Now we'll just finish off the reaction first, the system first. It goes down here. That steam turbine will connect to a generator, which will spin that, which will generate electricity, which, as I mentioned earlier, is our product. Now, the water that's boiled in this process here, after it's spun the steam turbine, it will need to be condensed. It'll need to be cooled down and turned back into liquid water. Now, that liquid water, which is a byproduct. Yeah, byproduct. I need a new color, don't I? Here we go. Let's pick a nice lilac-y color. So this steam, the water from the steam turbine that has to condense in the condenser, like it has to turn back into a liquid, that water is a byproduct which can go back into the boiler as liquid water, which can then be heated up by further fossil fuel combustion reactions. Now, as it's condensing, it's going to lose heat, and we use this in the condenser. It does this using what's called a heat exchanger. So you cool this water down, but you have to transfer that heat somewhere. That heat is going to go into, will be taken away as hot water, and that hot water can be cooled down in what's called a cooling tower. So those gigantic things, often you see them sort of on nuclear power plants or something. So those are cooling towers. Now just note, this hot water here in this case is a waste product. It's not being used, but that doesn't mean it could never be used. So in that same exam, they show you a modification of this where instead of into a cooling tower, this will go into a thermal desalination plant where they heat up water, salty water like ocean water, and boil away the water, generating desalinated water. So just because it's a waste product here doesn't mean it always is. Now this is a particular chart for a particular process. Every process will look unique. They'll have their own stages in these squares. They'll have their own bits and pieces. They'll have their own processes, their own reused materials, their own waste materials sticking out of it. The more you understand chemistry, the more you'll be able to understand whichever flowcharts you see. Okay, now moving into the next bit. Now here again, more chemical engineering sort of stuff. We need to consider some of the things that we've learned earlier in this chapter for the purpose of optimizing reactions. So getting reactions to happen so that we get the most of our desired product out of it, which most of the time means that you are going to be able to sell it for more money and make profit. Now the first thing we have to worry about is something called yield. Now yield just tells us how much of our stuff we're making compared to how much we could make. So how efficient is our process? Let's say we put in a certain amount of reactants which could make a certain amount of products. How much product do you actually get out? Now you calculate that using this equation here. So the percentage yield is going to be the actual yield, so how much of that final product you get out of it, divided by our theoretical yield, which is the maximum possible, and you multiply that by 100. Now the actual yield will be given to you. They'll say this is how much you've made. Now the theoretical yield you may have to calculate using stoichiometry. So if you are told you have this much of this reactant, this much of the other reactant, if you combine them together, how much of your product could you potentially make? You'll need to make sure you convert them into moles, and then work out how many moles of your product you could make, and then convert it into kilograms or whatever mass you're using. Regardless, if you find out how much you could potentially make, you can then use this equation to work out how much you've made. Just a really simple example. If you make 5 kilograms, but you could have made 10 kilograms, then multiply that by 100, you end up with 50%. Now, yield is one aspect. Now, or an aspect that you're trying to maximize. Now, one factor you can change in a reaction that will have an effect on the economics, like how much money you can make, will be pressure. Now, if you have a reaction container, and it's full of gaseous reaction particles, you can mess with the pressure of this. So you can add more of your gases, you can squeeze the container down to increase the pressure. Now, depending on this particular reaction you're looking at, this will have certain effects. Now, here is a generic equation. So we have chemical A, chemical B, and chemical C, and we have the stoichiometric coefficients in front of them there. for a reaction, if your A and B, so the sum of those two numbers, A plus B, is greater than C, in other words, there are more molecules on the left-hand side overall than there are on the right-hand side, an increase in pressure will result in our reaction being pushed to the right. So in other words, if we have fewer product molecules, an increase in pressure using according to Le Chatelier's principle, it will try and move the reaction forward to the side with fewer number of molecules. So if that was the case and we have our product here we're trying to make, increasing pressure would increase the yield. It would let us have, at equilibrium, we would have more of our final product. Now, there is a caveat. You can't just increase the pressure as much as you want. The reaction containers will have a pressure rating, so you can only pressurize them so much before they break. And if you want to have higher pressure containers, those containers are going to cost money, going to cost extra to actually have. Another thing is increasing the pressure by pumping in more of your substances. That is going to use a pump, and those pumps use electricity. So there's always going to be those costs involved as well. Usually the most common thing you're going to mention is the high pressure equipment is expensive, and if any of them fail, you now have a container that has really, really high pressures inside it. If it fails, it's essentially like a small bomb. So they are more dangerous. Cool. Now, each of these things are going to cost them some money, and you wouldn't, if you were doing this process, as a chemist, you would need to consider the increased costs involved with getting your reaction pressures high and work out if that's going to be worth it or not. Sometimes it will, sometimes it won't. Sometimes you can increase the pressure, it'll cost a bit more to do, but you get a lot more of your product out. Other times you may get barely any extra product out, so it's not worth it to increase the pressure. Now we'll move down to the next factor, which is temperature. Now, from the earlier subtopic, that temperature can have an effect on equilibrium rate. It can have an effect on the rate of reaction as well as the reaction equilibriums. Now, depending on the reaction, you're going to see overall different scenario. But first things first, if you have higher temperatures, it is going to make your reactions happen faster. So no matter what, if you have a higher temperature, your equilibriums, your forwards and backwards reactions will happen faster. Your equilibrium, whatever equilibrium position your reaction has, it will be established more quickly. And as they say, time is money. So if you can get your reaction done and dusted more quickly, then you could potentially be making more product per unit time, and it may end up being more profitable to do that. Now, there is a situation though when increased temperature can reduce yield. If you have an exothermic reactions that make heat, according to Le Chatelier's principle, if you increase the temperature of that reaction, it's going to try and reduce the heat by moving in the endothermic direction, which is backwards. And if you move backwards, that means you're going to make less of your product. Your yield percentage is going to reduce. But I'll say it here. So the deal is that increasing temperature can make your reaction happen faster, but it can, depending on the reaction, make your yield lower. There is going to be some balance in those situations as well. Sometimes, you might lose some yield, but the reaction happens so much faster that you're still going to make more product in a certain amount of time. You may need your temperature just go up a certain amount. So you might increase the temperature a little bit so that your speed is increased, but your yield isn't reduced too much. If you increase the temperature more, you might get the reaction happening faster again, but you may lose too much yield. It's all about sort of a give and take. If you reduce the reaction speed from 10 hours to 1 hour and your yield drops by 10%, that might be worth it. If you increase the temperature again and drop it from an hour to 30 minutes, but you drop, another 10% yield, that might not be worth it because the amount of time you're saving is only relatively small. Either way, you can summarize this as being the two situations. So exothermic reactions, if you increase the temperature, they will go faster, but you'll decrease the yield. Endothermic reactions, however, get faster again, but you also get an increased yield. So these ones here, these ones in endothermic reaction, they are just going to be beneficial if you increase the temperature. Again, you can't do that forever because some reactions are going to, first of all, heating costs money. Electricity costs money, depending on where that electricity comes from. If that electricity is coming from like a fossil fuel generator, then that means you're going to be impacting the environment negatively by using more of that energy. Regardless, heating does cost money, so the benefits will need to be weighed. So you go, I'm getting a benefit even for my endothermic reaction, which I need more temperature. Higher temperature is good. It may be that putting in so much heat costs too much money and it eats into your profits too much. So either way, you're trying to look for some sort of optimized result. Now, finally, we're going to look at catalysts. Now, we have looked at catalysts before. We looked at them all the way back in probably subtopic 1.1, so all the way back at the start. What they do is they increase the speed of a reaction. So before we used to think of them as just forward reactions, but now we know that forward and backward are both happening. So it's going to increase the speed at which the equilibrium is established. It does that just by providing some other pathway with a lower activation energy barrier. Now, using a catalyst makes reactions faster. It means you don't have to heat them as much. And this could potentially reduce the costs, as I mentioned earlier. You don't have to heat them up, so it could cost you less money. The one thing to worry about is the catalysts can be expensive themselves. So when they are used, they're often ground up into a fine powder, so that the surface area of those catalysts are maximized. That way, you're using every little tiny, as many atoms of that catalyst as possible at every moment. Now, one thing to consider over here is that catalysts increase the speed of reactions, but then they themselves are not used up in their reaction. That means they can be reused, but they cannot be reused forever because often in these reactions there's going to be some sort of impurities or some sort of contaminants, and they often will end up binding somewhat irreversibly to your catalyst, and that is called fouling. So when your catalyst is fouled up, then it can't be used anymore. You may have to process it, which itself can cost some extra money. So you can't just use them over and over again forever. Now, to end this subtopic, I'm just going to make a final statement, and that is that all the factors we've talked about previously, so we've got our our pressure, our temperature, and our use of catalysts, you need to consider all of them in a reaction to optimize production. So you're trying to make as much of the stuff as you possibly can, as fast as you can, as cheaply as you can, but not all these factors can be tuned without having to worry about things like cost or speed or safety. So you're trying to make things as fast as possible, you're trying to get as much yield as you can as possible, but overall the cost and the profit is what's going to be the biggest, is probably going to be one of the biggest factors, along with safety. So if something can be made as fast as possible with as much stuff as possible, but it costs too much to do so, then it's not worth it. So you're always going to be trying to optimize all these things to get the best result. Cool, have fun.